Hello there, Mr. Sutton bringing you this lesson on linearization. In this one, we're going to be approximating values of nonlinear functions using tangent lines. And as an application, you're going to be able to approximate pretty much anything you want without using a calculator.
For your warm-up, suppose we use tangent lines to approximate the function below at the labeled points. Draw those tangent lines and decide if each one will under or overestimate the nearby values. Based on those, what feature of a graph determines if its tangent line, L of x, we'll call that, is over or under? So pause the video and give that a shot. All right, let's look at our tangent line for A. So here's our tangent line, and that is definitely under approximating all the nearby values. Tangent line at B, also under approximating. Tangent line at C, over approximating. And the D tangent line right here is also an over approximation. So taking a look at this, it looks like the parts of the graph that are concave up will result in an under approximation, while the concave down part results in an over approximation. So concave up, in other words, f double prime is greater than 0, we're underestimating. And if you're concave down, we are overestimating. Notice that it has nothing to do with increasing or decreasing. It's all about the concavity.
Now that we've talked about the relationship between linear approximation and concavity, let's decide whether a linear approximation of each of these functions from the given A value would over or under approximate the function value. We'll do the first one together, and then I'll have you guys try the next two. So for this first one, we're trying to approximate f of 2.5 from a point of tangency of x equals 2, and we're also given that f double prime is positive on the interval from 0 to 6. So I have to look at the interval between my point of tangency, 2, and my input value, 2.5. On the interval for 2 to 2.5, f double prime, that's included in this 0 to 6 interval, so f double prime is telling us that our function is concave up on this interval. Therefore, we can conclude that L of x, our linear approximation, is going to under approximate that. All right, pause the video and try out the next two. All right, so for this one, we're trying to approximate negative 3.1 from A equals 1, negative 1. And we see that we're concave down all the way from negative 1 to negative 4. So that includes the interval from negative 3.1 to negative 1. We know that interval will also concave down for the g function. Therefore, L of x is going to over approximate on that one. And now for this last one, we're trying to approximate h of 4 from A equals 2. So that's the interval from 2 to 4 that we have to look at. Taking a look here, we see that we are concave down for the interval from 1 to 3, but that doesn't actually tell us about the whole interval. We're definitely concave down for some of the interval in between these, but we don't have enough information about concavity on the whole interval to make a judgment call one way or another.
For our next problem, we'll find the linearization of this function at this given value. Now what we're asking for here is the equation of a tangent line, and you could use point slope to give this. You could find the slope of the tangent line and the point that it goes through. Or you could use this specialized formula that everybody else uses, L of x equals f of a plus f prime of a times x minus a. Here it is again, in case you didn't see it. What we're basically doing here, this is kind of like point slope. This f of a is basically the y1. L of x is kind of the y, so it's like a y minus y1, but we put the y1 over here. F prime of a, that is the slope of your tangent line at a specific x value. And this a in here is kind of like the x1 from point slope. This is basically x minus x1. So it's really just point slope dressed up a little bit. Now to find these different things, let's start with f prime of a, the slope of the tangent line. First, we need to find just a formula for the slope of our function. So that would be 15 parentheses x plus, or 1 plus x to the 14th power. And then plugging in the x value 0, because that's where our tangent line is going through, we've got 15 parentheses 1 plus 0 to the 14th. That's just 15 times 1, or 15. Next, we're going to go ahead and find f of a, which in this case is f of 0. That's just going to be 1 plus 0 to the 15th power, which is just 1. And finally, a, they gave us that. That's 0. So putting it all together, we have 1 plus 15 parentheses x minus 0.
For our last example, we're going to go a little bit beyond what we did on the last problem. Instead of writing the equation of a tangent line, now we're going to use a tangent line at a equals 16 to figure out f of 14 for the square root function. So we're basically going to plug a value into our tangent line after we have written it. So pause the video and see if you can write the tangent line with these conditions, and then we'll go from there. All right, so to start this off, let me just write out my general formula. That's L of x equals f of a plus f prime of a times x minus a. It's a good one to have memorized, even if you have point slope ready to go. This one's a little more specific. Now let's figure out the different pieces we need for this. So we're going to need to know what the derivative is of our f function. I'm going to rewrite this as x to the 1/2 power, and then the derivative of that, we've got 1/2 x to the negative 1/2. And now let me find f prime of a and then f of a, and we'll go from there. So a in this problem, they told us, is 16. So if I plug 16 into my derivative, I'm essentially doing 1 over 2 times the square root of 16, which is 1 over 2 times 4, or 1 over 8. Next, we need to figure out f of a, which is f of 16 on this one. That's the square root of 16, which is 4. And you actually don't have to simplify any of this stuff for a free response problem, but again, if it's a multiple choice question, you will need to have it all simplified. So let's plug things in now. We can write L of x equals 4, that's f of a, plus 1 over 8, that was f prime of a, times x minus, what was our a value? Oh yeah, 16. So there we go. Now we have one more step here. We wanted to know the value of the function at x equals 14. So we're going to plug 14 in for x here. And if I do this now, I can simplify it if I wanted to. So this is going to be 1/8 times negative 2, which is negative 1/4. And 4 minus that is 3 3/4, or 3.75, or you could write this as, let's see here, 3 times 4 is 12, plus 3 is 15, so 15/4. So that's it for this one, except for there is actually one more thing. So you might think it's kind of weird writing L of 14. Maybe you wanted to go back and write f of 14, because they told you to find f of 14. So here's the thing. What you just found here is not f of 14, right? This is an approximation. It's not the true value of f of 14. So if you want to use the original function name instead of L, if you want to write f of 14, you need to write a approximately equal sign to show that it is an approximation. So if you wrote f of 14 is approximately equal to 3 3/4, that would be okay. If you wrote plain old equals here, that would be mathematically incorrect, and you would lose points for that. So that is it for this one. Hopefully you approximately understand what you're doing. True understanding will come from doing the homework, but until next time, this is Mr. Sutton signing off.